Hello, I'm Louis Wagasback, Thermal Analysis Product Manager at TA Instruments. I would like to welcome you and thank you for joining us in today's webinar. If you get disconnected at any time, please use the instructions you received to log back in. You can access various content by clicking the Documents widget at the bottom right-hand corner of the screen. This includes speaker bio and additional file downloads. If you need help at any time, click the question mark widget. Please ask any questions you may have at any time during this presentation by submitting them through the Q&A window. We will answer as many of these as possible at the end of the webinar. Our presenter today is Dr. Kadeen Mohammed. Dr. Mohammed holds a PhD in Materials Chemistry from the University of South Florida. Dr. Mohammed's doctoral dissertation focused on the development and thermal characterization of biocompatible polymeric coatings for an implantable glucose sensor. Kadeen joined TA Instruments in 2006 as an applications engineer supporting thermal analysis and microcalorimetry products. She became applications laboratory manager in 2014, where she and her team assist our worldwide support network. The title of her webinar is Characterization of Amorphous Pharmaceuticals by DSC Analysis. Kadeen?
Thank you, Louis. In today's presentation, I'll focus on using the DSC for the characterization of amorphous content of pharmaceutical materials. In pharmaceuticals, there are various thermal analysis tools that can be used to determine various parameters of that material. Firstly, we can look at, very briefly, the thermogravimetric analysis, TGA. With TGA, we look at a material's weight stability with respect to time, temperature, and environment. If we're looking to begin to heat that sample through a temperature range, if the material has a certain amount of organic or water vapor content, we're going to see a weight change associated with this. So you continue to heat the sample, the material begins to degrade. We have, with the TGAs, been able to determine weight losses as low as 10 to 15 micrograms of weight change in very small sample sizes, which can be of value in pharmaceutical analysis. As off-gases are evolved from the sample, if the material or the technique is connected to an FTIR or a mass spec, we can begin to chemically identify the gases coming off. Another tool that's commonly used would be dynamic vapor absorption. Water content as well as organic vapor content can have a significant impact in the physical and stability properties of a material. So with this technique, we're looking at the amount of uptake occurs of water vapor, organic vapor in a material at an isothermal temperature, and can determine the desorption and absorption profile as well as the isosorption profile of the material. The technique that we're going to focus on today would be differential scanning calorimetry, specifically with the detection of the glass transition and amorphous content. Although the DSC is very commonly used as well to look at the melt transitions associated with various polymorphic forms within the sample. Microcalorimetry as a technique is often used for the stability and compatibility testing of the API with the polymer matrix. So common DSC applications for pharmaceuticals. First and foremost, we're looking at amorphous structure of the glass transition. And this information can be quite useful, especially in the optimization of the freeze-drying process. And we're going to focus or touch on the freeze-drying process today. Commonly detected as well would be the crystalline structure, so melting and crystallization temperatures of the API and various polymorphic forms. The DSC can also be used to look at the purity analysis of a pharmaceutical drug. So what is a DSC? What is differential scanning calorimetry? This is a technique which measures the difference in the heat flow rate between a sample and inert reference as a function of time and temperature. If we were to break this down into simple terms, looking at Ohm's law. Ohm's law is a relationship of current and voltage. The DSC is a fixed current instrument. The thermocouple plates output a signal in voltage. And so from this, we can calculate the power. And that's your y-axis signal. We're looking at watts normalized to the initial mass of the sample. So power, when integrated with respect to time, gives us an output of joules. And this is where we're able to determine what is the enthalpy of melt or crystallization of a sample by integrating the heat flow signal with respect to time. Here we have a composite graph, an example of the y-axis being heat flow versus temperature. And in this particular case, we're showing that exothermic events are going up, endothermic events will go down. So with endothermic events, where you have, in order to have that transition occur, heat must flow into the sample. We see an indication here of a glass transition, as well as an endothermic peak. This peak, in this particular case, is associated with the melt transition of the sample, although in pharmaceuticals, we can often see endothermic peaks associated with the decomposition of the material as well. In this plot, we're showing an indication of the exothermic events occurring within the sample. So in this particular case, the amorphous content, as the material has gone through the glass transition and has more added molecular mobility, can begin to rearrange and crystallize. That's what's occurring right there around 100 degrees, followed by another exothermic event, which can be further crystallization or polymorphic conversion of one crystalline form to another. And at 150 degrees and above, we have a melt transition associated with the crystalline content. So those were some examples of what transitions might look like. But here let's focus on the DSC heat flow equation. If you understand this equation, it can help you with optimization of your experimental conditions. On the left portion of left side of the equation, you have the DSC heat flow rate. And that is equal to the summary or sum of two components. The first component there being the specific heat capacity change in the material, and then the next component would be kinetic events that occur at an absolute temperature and time. Notice that in the heat capacity component, the amount of heat flow rate that's generated associated with the specific heat change in the sample is directly proportional to the hidden rate of your DSC test. So with this, the correlation would be, if I have a sample in which the crystalline content is high, the amorphous content is low, and I'm looking to determine the amorphous content, the glass transition of this material, I have the options here through this equation to increase the hidden rate of the experiment, which will allow me to get more heat flow associated with the heat capacity component, as well as increase the sample mass, which is part of the specific heat parameter. So increased sensitivity in the ability to detect a glass transition can be increased through the use of changing your experimental hidden rate and increasing the sample size. With a purely amorphous material, no crystalline content, something that's not cross-linked, you can use standard DSC conditions of anywhere from 1 to 10 milligrams of sample, 5 to 10 or 20 degrees C per minute hidden rate should be able to detect your glass transition. As you increase your sample mass as well as the hidden rate, note that the breadth or the width of the glass transition region will become wider with these increased parameters. So your resolution goes down, whereas your sensitivity, the ability to see the transition, goes up. And that's something to keep in mind, especially if you're trying to deconvolute the step change associated with the glass transition from other events that may occur at slightly higher temperatures. The glass transition. So just a brief definition of the glass transition. What is the glass transition? It's a step change in the free volume and molecular mobility in the amorphous phase within a material. That results in the step change in heat capacity. So below the glass transition, the material is rigid and glassy. You have little to no long-range molecular mobility. You have a disordered solid. Going through the glass transition, which is a second-order transition, your material now goes into its rubbery flow. It has increased molecular mobility. So here is an example of an overlay between the heat capacity signal of the material as well as the heat flow over a temperature range where the sample undergoes a glass transition. Notice that below the glass transition, there are parameters that will become reversed once you go through the TG. An example would be below the TG, you have a lower specific heat capacity value. You have lower free volume, lower coefficient of thermal stability. The material has a higher stiffness and viscosity. As you go through the TG and above that value, now the heat capacity increases, the coefficient of thermal expansion increases, the material is less stiff and has a lower viscosity. So you can see that the TG, the glass transition, has a significant impact on the physical parameters or properties of the material. And it may have an impact on the chemical stability of the material as well. So it's important to be able to detect the glass transition and understand where that value occurs. With amorphous materials, the glass transition, or with amorphous materials, I should say, you increase the rate of degradation, water absorption, and dissolution. The increase in the rate of dissolution, for instance, might be an added benefit in being able to quickly dissolve an amorphous pharmaceutical. However, it leads to a faster rate of degradation. So there's always a balance between finding what's the right temperature, especially with respect to the storage conditions, the use temperature of a material, to minimize degradation while the material is being stored and prior to the use of that material. Water can have a plasticizing effect on the glass transition of pharmaceutical materials. It can change the TG or shift the TG to low values quite significantly with very little water content. There's typically an initial or very rapid reduction in the TG with very small amounts of water content. And then as you keep increasing the water content, then there is a gradual leveling off in the response of the TG or the shift in the TG. The DSC, as well as coupled to the vapor sorption analyzers such as the Q5000 SA, can be used to give you both of these parameters. What's the sorption isotherm, water content, and then placing that sample on a DSC to determine the TG. So here's an example of the plasticizing effect of water on a material, and we're looking at amorphous sucrose. So on the first heat cycle, the glass transition occurs around minus 28 degrees Celsius. As we begin to heat that sample through the TG, notice that as we approach 100 degrees, in a DSC pan which is not hermetically sealed, so there is a standard lid, it allows evolution or evaporation of water from that sample out of the pan, effectively drying the sample to a low water content. And that evolution of water content or evaporation is observed by that endothermic peak that occurs around 70 degrees Celsius. As that sample is then cooled and reheated, notice on the second heat cycle, the glass transition has now shifted to approximately 12 degrees Celsius. So now with the lower water content, the TG is at a higher value. So understanding the impact of water on the TG can have an impact or significance in how that material is stored, how it may be transported, and so on. So with the understanding that water content can impact the TG value, it's important that you determine what's the best way in which to prepare the sample in your DSC pan, or how do you encapsulate your sample in a DSC pan to be tested on the instrument. So if you would like to determine the glass transition of the material with that water content, let's say your sample has 5% water content, and you would like to know what is the TG of that material as is, the ideal approach would be to hermetically seal that sample in the DSC pan, keeping the environment within the pan consistent, and not allowing the water content to evaporate out of the sample pan. If you would like to know what is the glass transition of the dry sample, you may consider doing a heat, cool, reheat test, where on the first heat you're driving off the water content. Placing a few pinholes into the lid of the pan can help facilitate the evaporation process. And then cool the sample down, reheat the sample, and look at the glass transition on that second heat. So with this, let's look at some practical approaches to preparing the samples. We have here the T0 press, and with it you have the options for different die sets. Here we're demonstrating or showing the T0 aluminum pans, and these come in standard T0 pans or the T0 low mass pans. The T0 pan has approximately 40 microliters of volume, whereas the T0 low mass pan is about half of that. The low mass pan is used whenever you have a very limited amount of sample and would like the highest amount of sensitivity in being able to detect your transition. So with the low mass pan, you have less resistance to heat flow associated with the pan itself. Other pans are available, so there are gold pans, stainless steel pans, as well as copper pans. So various pans are available depending on whether or not your sample will interact with that particular pan. The T0 aluminum pans can be used with a combination of two different lids. We have the T0 lid, which is a standard lid. It does not create a hermetic seal. And then the T0 hermetic lid, which creates a hermetic seal. The hermetic lid prevents the evaporation of moisture content or organic solvent content from your pan. As you begin to heat a sample, that water content will still evolve out of your sample, but will begin to build in the headspace within the pan. And the maximum internal pressure rating for this lid configuration would be about 2 to 3 atmospheres. So here we have a bit of an example of the powder preparation tool. This is a tool I use quite often, especially when preparing samples that are affected by static. So we've tested samples before. As you put the sample in, it immediately jumps out, which makes it quite frustrating to prepare that material in a DSC aluminum pan. This particular tool utilizes a funnel as well as a plunger to very effectively, efficiently, and cleanly get sample into the pan without getting a bit of contamination on the lip of the pan, thereby allowing you to get a proper hermetic seal between the lid and the pan if needed. For a full version of that TA Tech Tip video, please visit our website or YouTube channel. Now that we've covered sample preparation, let's look at DSC method development. With a DSC experiment, you can define what start temperature you would like to begin the test. So here I have the first segment is equilibrate to a certain temperature. Now you may start your test at room temperature and then begin a temperature ramp up if your glass transition is above room temperature. However, for frozen liquid solutions or materials that may have a sub-ambient glass transition, you may want to start your test at temperatures that are below room temperature. The liquid nitrogen accessory allows you to start the test at minus 180 degrees Celsius, or if you have the refrigerated cooling systems, you can start as low as minus 90 degrees Celsius. The next segment would define the heating rate as well as the upper temperature limit. As mentioned earlier today, the heating rate can impact the sensitivity of the measurement. So if you have a material that is highly crystalline with very little amorphous content, you may want to increase the heating rate to amplify the signal associated with the glass transition step change. However, typical heating rates can range from 5, 10, 20 degrees Celsius per minute. The upper temperature limit of the temperature ramp can be dictated by the decomposition temperature of your sample. So if your material begins to decompose at 150 degrees Celsius, you may want to ramp through the TG to a temperature above the TG, but stay below the decomposition temperature. Sometimes the DSC can be used to determine what is the decomposition temperature of a material. In that case, you may heat through decomposition. The material may go through an endothermic or exothermic process for decomposition. If you plan on doing a heat, cool, reheat cycle, that first heat cycle should stay below the decomposition temperature. Now let's look at an analysis of the glass transition through DSC. Notice here on the y-axis you have heat flow, exothermic events up, endothermic events down versus temperature. We're demonstrating all of the labels that can be placed on an analysis. First, starting with your analysis temperature region, the selected start and selected end temperatures are used as selectable. So you define the start or the range on the baseline where you would place your analysis cursors. Next, what's defined would be the slope of the step change, and from that we get an intersection of the extrapolated onset, which is the tangent to the slope, and the tangent to the selected start region, and as well as the extrapolated end set. The extrapolated end set is an intersection between the tangent of the slope and the tangent of the selected end position. The extrapolated onset and end set gives you the width or the breadth of the glass transition. And things such as the molecular weight distribution can certainly impact the width or the breadth of the glass transition. Also defined here would be the glass transition temperature, which would be the midpoint. So as analyzed here, we have the TG being representative as the midpoint at the half CP, or the half step change of this transition. With the glass transition analysis, in addition to getting temperature values for your analysis, we can also define what is the delta CP, or the change in heat capacity of that glass transition step change. And this is a very useful parameter because it can allow us to quantify the amorphous content in certain compositions. And let's look at that. So the quantification of amorphous materials in semi-crystalline samples. Let's say I have some amount of amorphous lactose in a generally crystalline lactose preparation. The size of the glass transition, or the size of the step change of the heat capacity, the delta CP, is typically linearly proportional to the amount of amorphous structure within that sample. This is certainly the case if the glass transition or the amorphous content is available and not within the rigid amorphous phase. If the amorphous content is part of the rigid amorphous phase, then that amorphous phase does not contribute significantly to the step change of the TG. Certainly not as much to the delta CP or change in CP associated with the glass transition. So as you can see, this type of analysis would be for certain types of materials and morphologies. In this particular example, we have a material that has been quench cooled from its melt. So a sample is taken above its melt transition, and now that it is in its molten or liquid amorphous state, it is then quickly quenched to temperatures below the glass transition. Quickly quenching a material can inhibit or delay the onset of crystallization on cooling, thereby creating, at the end of the quenching process, a material that is now in its solid amorphous state. This solid amorphous state, this 100% amorphous content material, will then undergo quite a large step change associated with the TG. And from here, the blue line, where we're looking at the glass transition of a material that has been quench cooled, notice that the step change is about 0.55 joules per gram degree C. So this is the delta CP for 100% amorphous content. If I have a sample of which I would like to know what is the amorphous content, let's say that sample would be the green line. Notice that's a sample that has been slowly cooled from its molten state. So as we slowly cool a material, we allow it, if it has the tendency to crystallize, we allow that material to crystallize. And therefore, at the end of that cooling process, we may have a material that is more crystalline and less amorphous. And the step change associated with the glass transition, which occurs at 24 degrees Celsius, is very small. Notice that it is 0.03 joules per gram degree C. To determine what is the percent amorphous content, now that we know what is the delta CP for 100% amorphous material, the percent amorphous content of this sample that has been slow cooled would be 0.03 divided by 0.55 multiplied by 100 to get a percentage. And in this case here, we find that this sample has a 6% amorphous content. This is one of the ways in which we can use the DSC to quantify amorphous content. Here is another example, very similar to the one before, except we're looking at the y-axis in terms of a heat capacity signal instead of heat flow. And as a material goes through the glass transition, we see a step increase in the heat capacity or specific heat capacity. We're looking at examples here of a material that is 5% by weight amorphous content, 2.5% by weight amorphous content, as well as 1%. And notice that the delta CP, the change in heat capacity for each of these would be, for the 1% amorphous content, 0.01 joules per gram degree C, for the 2.5, 0.02, and then for the 5% amorphous content, 0.04. If this were to be plotted on a scale where we're looking at delta CP with respect to percent amorphous content, notice that our theoretical line matches very closely to our experimental conditions. So certainly you can use DSC by first generating a calibration curve to then quantify the amorphous content of your materials after the manufacturing process. Now, by DSC, sometimes it can be difficult to detect the glass transition. If the material is highly crystalline, where the amorphous content is low, the DSC on its own may not have the sensitivity needed for the detection of the TG. In those cases, we may utilize other techniques such as modulated DSC as well as dynamic mechanical analysis. Dynamic mechanical analysis, in which we're looking at a change in the modulus of a sample through a temperature range, is certainly a technique that is the most sensitive technique compared to modulated or standard DSC in detecting the glass transition. Can you use the DMA to determine the glass transition of powdered samples? Absolutely. Using the powdered preparation or powdered clamp accessory on the 3-point bend dual cantilever on the DMA, you can certainly perform temperature ramps and determine the tan delta peak associated with the TG. But what we're going to look at for this presentation would be a focus on modulated DSC. And here's an example of the benefit of using modulated DSC. It's a scan of lactose, a powdered lactose, in which the green line represents the total heat flow. This would be the signal generated from standard DSC. And we're doing a temperature ramp from 40 degrees to 120 degrees. Notice in the total heat flow signal, you have an endothermic trend that peaks around 70 degrees, followed by a slight exotherm, and then what may appear as an endothermic peak around 100 degrees. This thermogram appears to be very difficult and convoluted to interpret. Modulated DSC will help us simplify the thermogram and allow us to better interpret the results. So by modulated DSC, where we separate the kinetic portion of the heat flow equation from the heat capacity component of the equation, we get two separate signals, the reversing heat flow signal, as well as the non-reversing heat flow signal. So looking at the non-reversing heat flow signal, notice that there is an endothermic peak occurring between 60 to 80 degrees, and this is very likely due to the evolution of water from the sample. Amorphous solids can certainly absorb water content from the atmosphere, and that water content is very loosely bound to the surface of the material. So on heat inlet, it's easily evolved and occurs as an endothermic change in the heat flow signal. As you continue to heat the sample, notice in the reversing heat flow signal, you now see a clearly defined glass transition at 116 degrees. Superimposed on that glass transition would be an enthalpic recovery peak, which is a kinetic event certainly associated with the storage conditions of the material. So going back to the original heat flow equation so that we can better understand how modulated DSC is applied. The heat flow rate on the left component of that equation is equal to a heat capacity component plus kinetic events. Notice that the heat capacity component, when multiplied by the heat and rate, will generate a heat flow associated with events such as the glass transition. In a modulated experiment, we modulate the heat and rate to a point where the heat and rate approaches, goes to 0 degrees C per minute. When the heat and rate goes to 0 degrees C per minute, if the DSC detects a heat flow signal at that point, then the cause for that heat flow would be due to kinetic events taking place in the sample, which falls into the non-reversing heat flow signal. This would include events such as enthalpic recovery, evaporation, crystallization, denaturation, decomposition, and some melting. Here we look at the instantaneous heat and rate equation for modulated DSC. Notice with this equation, the user has to define certain parameters. So the beta symbol of the equation would be the underlying heat and rate. Typically, we can set a heat and rate of 1 to 3 degrees C per minute. You can go slower, you can go a bit higher than that as well, but the instantaneous heat and rate or average heat and rate has to be defined in the software, followed with a definition of the amplitude as well as the period or the time it takes to complete one modulation cycle. So as these parameters are input into the equation, the final instantaneous heat and rate will be determined and applied to the experiment. In this case, we're looking at the heat-only conditions in which the heat and rate, the instantaneous heat and rate, approaches 0 degrees C per minute, but does not go below that value. And the conditions are set through the amplitude, the period, and the maximum or average heat and rate. These conditions are ideal when looking at materials that are semi-crystalline or crystalline. The other conditions would be conventional MDSC, where the amplitude is set to be high enough where the instantaneous heat-in rate approaches 0 degrees C per minute, but then also goes into negative heat-in rates, or essentially cooling rates. So the sample temperature on average will increase, but if you look at the individual sample temperature, it increases and decreases, increases and decreases. And these are conditions that are ideal when looking at detection of a very weak glass transition, as well as the determination of the specific heat capacity of the sample. So some guidelines for determining the glass transition of amorphous materials. And certainly these are guidelines. You can choose to edit these numbers as needed, depending on your sample. So for the period, which is once again the time it takes to complete one full modulation cycle, for the low mass pen, which weighs about 50% less than the T0 pen, it offers less resistance to heat flow and is oftentimes used when the highest level of sensitivity is needed in detecting your transition. For these pen types, you may use a period of 40 seconds or 60 seconds, so anywhere around 40 to 60 seconds. For the T0 pens, which weigh approximately 50 milligrams, a good start-in period would be 60 seconds, but you can certainly use something that is higher than that, so 60, 80, even 100 seconds as your modulation period. The minimum period depends on the pan type and the pan mass. The amplitude, when looking for the glass transition, we would like to stay within the conventional MDSC test conditions. So notice here we're using quite a large amplitude. If I were to perform a test, let's say at 60-second period modulation, an amplitude of 1 degree C and a heat-in rate of 3 degrees C per minute, and I still have a very difficult time finding the glass transition, an option for me would be to increase the amplitude. Increase in the amplitude increases the sensitivity to the detection of the glass transition. And then finally, as the user, you have to define what the average heat-in rate will be. On average, we're using heat-in rates from 1 to 5 degrees C per minute. However, the value used would depend on the width or breadth of your glass transition region. Typically, you want to have approximately 4 to 5 modulation cycles through the step change of the glass transition. And this may sometimes necessitate you having to slow down your heat-in rate. So now that we've looked at sample preparation as well as method development, let's look at an example of where knowledge of the glass transition is important for the manufacturing process. And in this case, we're going to look at the process of freeze drying. With freeze drying, you have a solution, a buffer solution with solid analytes, whether it's proteins, drugs, and various other additives and fillers. That solution is then cooled to a temperature where it's now in the frozen state. In the frozen state, in the process of lyophilization, a vacuum is pulled and sublimation occurs, leaving behind a solid cake. The process of freeze drying, or that primary process of drying, requires that sublimation occurs at a temperature below the glass transition of the frozen solution. And that's where the DSC comes in as a handy tool for determining where is the glass transition of this frozen solution. And let's look at some examples. In this case, we have a DSC scan, standard DSC from minus 80 degrees to 60 degrees Celsius, where we're heating at an average heat-in rate of about 10 degrees C per minute. And notice what is immediately available to you is that large endothermic melt peak, and that's the melting of the bulk ice. However, the most important feature of this thermogram would be the step change associated with the glass transition, and this occurs at minus 24 degrees. Notice it's a very small step change, so therefore you will need to zoom into the baseline of the heat flow signal to find this glass transition. Sometimes it's not as easy to see the TG of a frozen solution. in which cases we may utilize modulated DSC. Here I would outline some test conditions that have been used for the next data file. The experimental conditions would be a T0 pan with a hermetic lid. With any liquid samples, you want to use a hermetic lid. The T0 pan can accommodate a volume of about 35 microliters, and in this case, I've selected anywhere from 10 to 30 microliters as the sample volume, followed by a method of subambient start temperature. Since you're looking at a frozen solution, you need to cool the sample to temperatures below freezing. So the sample test will begin at minus 80 degrees, and the modulation conditions used would be modulate plus or minus 5 degrees Celsius, which would be your amplitude every 60 seconds, and this is the period of the modulation, and the temperature ramp rate of 1 degree C per minute through the melt of the ice to 25 degrees Celsius. And let's look at an excerpt of this data file in which a 10% sucrose solution has been used. Approximately 10 microliters of volume was placed in the DSC pan. Here we have a sample mass of about 11.75 milligrams. And we're looking at 3 signals: heat flow, reversing heat flow, and non-reversing heat flow. First, an examination of the heat flow signal, which would be the black line. Notice that at minus 50 degrees, as you increase the temperature, you begin to see a step change, but then there is a slight exothermic trend or peak before the onset of the melt of the ice. The standard DSC heat flow signal can sometimes be complicated, and to better identify the glass transition and analyze that transition, modulated DSC will allow us to deconvolute or separate the glass transition, which would go into the reversing heat flow signal, from kinetic events such as crystallization. And that's exactly the case here, where the blue line, which shows the reversing heat flow, allows us to easily identify and analyze the glass transition, which occurs at minus 43.6 degrees, and then it's followed by an inflection that then leads into the melt of the ice. And then what's separated out of the total heat flow would be observed in a non-reversing heat flow, the red line, where we see a slight exothermic peak associated with crystal perfection. And so with that, we've come to the end of today's webinar. Feel free to reach out to us through the applications hotline. The email address is applications@tainstruments.com. You're also welcome to view our TA Tech Tip videos, which are released on a regular basis. Thank you.
Thank you, Kadeen, for that informative presentation. A recorded version of this webinar will be archived and available online through the TA Instruments website. We will now begin the question and answer segment of this webinar. Please submit your questions through the Q&A window. We will do our best to answer as many questions as possible.
Okay, the first question. What is the optimal heating rate of a DSC experiment when the pharmaceutical sample I'm working with is highly plasticized?
Hi, Louis. Thank you for that question. Okay, so that's a great question. When a material is plasticized, the glass transition will be a sum total of what is the TG and volume fraction of the active ingredient, as well as the TG in weight volume or volume fraction of the additive. And if that plasticizer, and it being a plasticizer, it's miscible with the pharmaceutical material, it's going to shift that TG. So you'll have a TG that will lie somewhere between the TG of the pharmaceutical sample and the TG of the additive or plasticizer itself. So the question is, what is the optimal heating rate? The plasticizer, in addition to shifting the glass transition to a lower value, it can certainly broaden the TG over a wide temperature range. And with that broadening of the TG, it may be difficult to really find that deviation from the heat capacity baseline the step change of the glass transition followed by the heat capacity baseline of the sample after the TG. So we can try to increase the heating rate to maximize the step change associated with the TG. So the question is, what is the optimal heating rate? It's a matter of trial and error. Let's say you start your test at 10 degrees C per minute and you're still having very weak broad transition, then increase that heating rate. Go ahead and take it up to 20 degrees C per minute. Sometimes I've worked with heating rates as high as 40 degrees C per minute to be able to get a good definition of that step change.
Okay, great. Thank you. Next question. Mixing amorphous polymer with semicrystalline polymer sometimes causes the disappearance of the TG. I found this in literature without clear explanation. Could you please explain why? Is it related to fragility of the mixture, and how to detect it in this case?
Okay, great. So the DSC is the total heat flow is giving you the sum total of the heat flow of all the components and all the events that are taking place. So let's say you have one component that is amorphous, the other one that is crystalline or semi-crystalline. If the amorphous content is of a low weight fraction or volume than the crystalline, then you're going to have less of a heat flow associated with that glass transition of the amorphous material or component in that mixture. So it boils down to, again, how do I increase the sensitivity in being able to detect a TG or a very weak TG? So going back to the heat flow rate equation, heat flow is equal to heat capacity multiplied by heating rate, which is where your TG, your glass transition, will fall into. Increasing the heating rate, increasing the sample mass, would be steps you can take as part of your experimental design. I have found that also in cases using a helium gas purge, which has a higher thermal conductivity and better heat transfer properties than the typical nitrogen gas that we would use for the DSC experiments, that can improve the ability or sensitivity in your measurement as well. Modulated DSC as a technique increases sensitivity and resolution. I would certainly give modulated DSC a try as well.
Okay, thank you. Could you discuss the differences in DSC results when using a reusable alumina pan that does not have a hermetic seal, such as pans used in the Q600 SDT, as opposed to a hermetic pan?
Okay, so with that question, you should ask first, do you want to test your sample with a hermetic seal or without a hermetic seal? So if the sample, amorphous solids, may contain a certain amount of adsorbed water that can possibly plasticize the TG. If you are interested in knowing what is the glass transition of a dry sample, then testing with a non-hermetic lid or no lid would be your option. So you can either dry the sample outside of the DSC or in the DSC by doing a heat-cool heat. The first heat dries off the water. The second heat gives you the glass transition of that dry solid. With alumina versus aluminum, so a ceramic pan versus aluminum, which we would typically use for the DSC, you're looking at differences there in its thermal conductivity properties. Alumina or ceramic is not as conductive as aluminum, so heat has to transfer from your sample through the DSC pan to the DSC sensor. So if your pan itself is not very conductive, you may lose some sensitivity in being able to see that transition as compared to aluminum or even materials such as gold or copper, but more so aluminum that is commonly used on the DSC, that has a very high thermal conductivity value, so the heat transfer path is optimized and you're not losing sensitivity in your measurement. If your sample is going to react with your pan material, let's say your sample is going to react with aluminum or gold or stainless steel. Is alumina, the ceramic pan, an option? Absolutely.
Okay, thank you.
I should say one last thing. You should always calibrate your instrument for temperature and cell constant. Cell constant being the response for the enthalpy or area of a peak that is calculated. The DSC should always be calibrated with your pan selection. So if you're running with alumina or ceramic pans, you should definitely calibrate with the indium standard using that pan type.
Okay, great. Here's another question. Does the powder preparation tool come with the dye kit, or is it purchased separately?
So it is not a standard part of the DSC, or I should say T0 press kit. It's a separate part number, and what we can do is include the part numbers on the resource link of this webinar once the webinar is complete.
Okay,
I would
great.
say that that powder prep tool has helped me tremendously. A lot of the pharmaceutical powders are very low density, so they're fluffy and light, may even have some static effects. So when you have a very fluffy, light powder, you're not getting a whole lot of mass into your DSC pan. So you may only be able to fit something like 0.5 milligram of sample into your DSC pan, just taking up that volume of the DSC pan. The powder prep tool, which uses a funnel and a plunger, it really allows you to compact your powder samples into the DSC pan, allowing you to get more material in there, more mass, so therefore being able to get more heat flow associated with the transitions that you're looking for.
Okay, great. Yeah, I agree. It's a great tool. Okay, next question. I see only one glass transition in my pharmaceutical blend, which has a few amorphous components. Why is this?
So if the amorphous components, in your blend, if you have multiple components, if any of them are miscible with each other, then the glass transition will follow the Fox-Fleury equation. And the Fox-Fleury equation ties in the glass transition of the blend is equal to, the weight fraction of component 1 or amorphous solid 1 multiplied by the TG of that amorphous solid plus the weight fraction of the second component multiplied by the glass transition of that second component. So it's going to be, it's a relationship which can be found in a lot of thermal analysis books. It's the Fox-Fleury equation. So if you're seeing, if the material is miscible, you would likely see just a single glass transition, and it falls in between, somewhere between the TG of component 1 and component 2. In other instances, it may be that if the materials are not miscible, but the glass transitions are very closely situated, so they're taking place in very similar temperature ranges, you're losing resolution and they're merging into each other. And a great way to see if it's truly miscible would be to perform a modulated experiment. Modulated experiment not only separates the glass transition from kinetic events, but if you have two closely occurring glass transitions in a narrow temperature range, Modulated DSC gives you resolution or separation of these two glass transitions. So I would say that an approach would be first run standard DSC, you see a single TG, you can then begin to assume that it's miscible, but to truly confirm that, run modulated DSC as well.
Okay, great. Kind of associated with that, modulated, we have a question here that you've sort of answered, but I think maybe a little clarification would be good. The question is, can a modulated DSC equipment work like a DSC equipment, or is a DSC equipment always more sensitive than modulated DSC?
So first, you would need to have a DSC. So a DSC with the capability to modulate the heating rate of that DSC cell or furnace. So modulated DSC is an option on a DSC. Lewis, I hope I answered that question. I don't know if there's any technical part beyond that.
No, I think that was good. That I think gave the point there. Thank you.
Mm-hmm.
Okay.
All TA DSCs are already designed to have the capacity to modulate the furnace. If you have a Q20, Q2000, or Discovery. Okay, great.
Here's a good question, I think, to make sure people understand. Do you add the sample pan at minus 180 or minus 80 or at ambient to start the equilibration? Sorry.
That's a great question. So let's say at room temperature, your sample, as you cool it down, is not going to go through any sort of crystallization. Let's say it's a solid at room temperature. Then if you were to place that sample pan into the cell at room temperature and then equilibrate down to minus 80 or minus 90 degrees, then your cooling rate as you cool from 25 to minus 80 is not going to impact any of your thermal events because the sample is not going through any crystallization on cooling. If you have a liquid sample and you want to, or even a wax-like material, and you know that it is a semi-liquid at room temperature, then as you place it in a DSC, you want to use a controlled cooling rate experiment so that you know what that crystallization event in kinetics, that you know it's controlled. It's controlled at the cooling rate you've set. You should never load a DSC pan at subambient temperatures, mainly because if you were to open the DSC lid and that cell has been cooled to minus 90 degrees, immediately the water in the atmosphere, the relative humidity in the room is going to begin to condense and then crystallize. So you're going to have freezing or frosting inside of the cell from the air or the water that's in the air. So always place your sample pan into the DSC cell at room temperature and then perform your equilibrate to subambient temperature program. With our DSCs, a lot of times our customers as well as our service engineers will install the DSC and then set a standby temperature of 40 degrees Celsius. And this is a great option, especially when you're not using the DSC often, or if you're turning off the gas purge to the instrument when it's not being used, to have that slightly higher elevated temperature to minimize any absorption of water into the DSC cell. So if your sample goes through low temperature transitions that occur very close to room temperature, then my suggestion would be to change that standby temperature to somewhere between 20 to 25 degrees. Standard laboratory conditions might be around 23, so change the standby temperature to 23 degrees and then load your sample into the cell.
Okay. Next question. Is there an overlap? If there is an overlap between melting and TG, is it possible to use modulated DSC to separate the events?
Mm-hmm. It is possible, but it comes with you needing to try out several different modulated conditions. So the glass transition falls into the heat capacity function of the equation, which is termed the reversing heat flow signal. Kinetic events like crystallization will always go into the non-reversing heat flow component or kinetic component of the equation. Melting, which is a latent heat, will fall into either the reversing heat flow or non-reversing heat flow signals. It's not a heat capacity change within the material, so it's not always completely deconvoluted from the glass transition. But I can tell you that if you were to use conditions where you make it a little bit more difficult for the sample to follow the modulations, then more of the melt will go into the non-reversing heat flow signal, and it will allow you to then deconvolute the glass transition from the melt. So what would be conditions that will make it a little bit more difficult for the sample to follow that modulation? Using a slightly larger sample mass, a faster heating rate, or a shorter period. Those are three of the conditions that you can use. But really, I would start off with some of the general guidelines that are listed on the template when you launch the software for heat iso modulated conditions, and then go from there.
Okay. We have time for one more question, and that is, thank you for the information presented today. However, I'd like to know if DSC can be used to perform purity analysis through the melting peak of a crystalline sample.
Yes, so I know this presentation focused mainly on the glass transition and amorphous content, and hopefully we'll be able to do another presentation where we cover polymorphism, crystalline melts, and purity. The answer to that question is yes. There is an ASTM standard. I believe the number is E928, ASTM E928, which uses the DSC to characterize the impurity content of materials where your purity is at least 98.5%. What you're looking at is heating the material through the melt transition, and during this melt you have to confirm that the material is not decomposing, that it's not losing weight, and so on. But as you perform this melt transition, impurities will cause a melt point depression, as well as will change the onset slope as it leads into the melt peak. So this ASTM standard focuses on integrating the area of this peak, but also creating fractionated or partial areas in the analysis leading into the peak. And from that area of partial area analysis, you can generate, from the Van 't Hoff's equation, an Arrhenius relationship. And from that Arrhenius relationship, the slope and the intercept can give you information such as what is your impurity level, as well as the expected melt point with this impurity. So the answer to that question is yes. It's really well defined in the ASTM standard. But if there are any specific questions that you would like to ask, certainly contact us at the applications helpline, and we can go through some experimental details.
Okay, great. So that's going to wrap up our question and answer session and bring to a close this webinar. Once again, I'd like to thank Kadeen for that excellent and informative presentation, and also for the question and answer session. I'm sorry we weren't able to get to all the questions, but if you either contact Kadeen or I offline or contact our thermal support line, we can help answer those questions for you. I'd also like to thank all the attendees for their participation and attention. Have a great day.
Thank you, Louis.